Hello students, welcome to the course Verilog HDL. In the previous two videos, we understood what is meant by gate level modeling and Verilog gate primitives we have understood, and also we have seen the two types of gates, AND OR gates and buff NOT gates. Okay, so with this idea, so we'll try to see some examples. So how we model an digital system design at the gate level. Okay. Having understood the various types of gates available in Verilog, we will discuss a real example that illustrate design of gate level digital circuits. Okay, so two examples we will consider here. So one is gate level multiplexer, a 4:1 mux we will consider. Okay, and then we will have a 4-bit triple carry full adder which will be constructed from a 1-bit full adder. So that's why we will first understand 1-bit full adder program, and that same program will be invoked here in this triple carry full adder. Okay, so this will be seen next video. So today's video will see focus on gate level multiplexer. Okay, so before we start this example, I will give you a one tip. Okay, so if you have any of the programs so you have to write, you need to follow some certain steps. Okay, that means you no need to by heart the program. For that, I told you in the previous video also, I will teach you no need to by heart the programs, so you that you can design and you can write your own program, such a method. Okay, so that's what I'm going to show you first. Okay, so this is the step. Okay, so how we proceed with writing and program. Okay, so very first, any design. Okay, so by default I will say now 4:1 mux, or I say full ladder, or I say flip-flop, or counter, anything. When I say, the first thing comes to your mind is the IO diagram. Okay, so IO diagram is the first thing should come to your mind. So if you come to know what is IO diagram, that means how many inputs are there, how many outputs are there for that design. Okay, it is also called as logic symbol. Okay, so once you know how many inputs are there, then based on the input combinations, you can write the truth table. Okay, so for example, if you have one input, okay, so how many combinations you will have? 2 to the power 1, 2 inputs, 0 and 1. If you have two inputs, then 2 to the power 2, 4 combinations, so you'll have 0 0 0 1 1 0 1 1. Similarly, if you have three inputs, 2 to the power 3, 8 combinations, so 0 0 0 to 1 1 1. Similar way you can draw the input part of the truth table. So how you write the output? Based on the functionality of that. Okay, the design, so that also you know. So based on that, so if adder is there, so just you have to add the inputs, and carry you have to note down, right? So you have to do the boolean addition. So from that you will get the output table. Okay, so once you get output from that, you can, if it is larger table, you apply the insert into kmap and get a simplified boolean expression. Or else if it is a simple one, you can, using the normal methodology, you can do the sum of products expression. Okay, so that is what you will get next. Once you know the truth table, so you'll come to the boolean expression or logic expression. Okay, so once boolean expression is known, so you can able to draw your gate level diagram, logic diagram we say. So based on the, so if you have dot, you'll have AND gate. If you have plus, you'll have OR gate. If you have complement, you'll have NOT gate, right? So these are the basic gates you have studied. Based on that, you can able to write logic diagram. And so these 4 steps are not new in this course. Okay, so this you have gone through digital system design course, and you have already done this, but again you require this knowledge to write your program very efficiently. Okay, so some of the course, so digital system design and Verilog is combined, because you should learn parallelly. But here, as an electronics course, you will be learning digital system design separately and Verilog HDL separately. Okay, so that's why you require the knowledge of that. So once you know the logic diagram, then you can write the Verilog description at gate level straight away, because so you know in logic diagram what are the gates are there, and you know now Verilog gate primitives for various gates. So just you call there with the instance name. Okay, for primitive gates, no instance name also required. Just you pass the what is the output and input. So your program is ready with first level of description. Okay, so similar way as we proceed. So below this gate level, you have switch level we mentioned, right? So switch level means you need to require one more diagram below logic diagram design. You should have a NMOS PMOS level circuits. Okay, in microelectronic subjects and all, you will be looking at that in VLSI subjects. Okay, so that is not required here. So gate level is sufficient. So above gate level is data flow. For data flow, even you don't require this logic diagram. Okay, if you know the Boolean expression, so you can able to write the program Verilog description at the data flow level. Similarly, if you know the truth table, okay, so you can draw the program at the behavioral level. Okay, so that is what about. Okay, so this concept I was explaining. So always whenever any program is given, directly don't jump to this step of writing the program with a by heart concept. Okay, so it will not work out. Okay, so all you are doing the simple examples here, but when you are doing in really industry, so that is the method. First you need to have the IO diagrams, how many inputs I want, outputs, which are connected, which are not connected, that should be clear. Once you know, you will write the truth table for that, because you need to verify the design at the end. Okay, then you have the Boolean expression, then based on that you will write the logic diagram. Once you know the logic diagram, you know the Verilog gate primitives, you are writing the gate level description. Okay, so this is what how you should do the program. So once you have done, so similarly you have to write the stimulus module to verify this output. So this also, if you write 2 or 3 programs, you will understand the normal step of writing. Okay, just the truth table we are writing here as an programming language. Okay, so just we'll see with this is also called as test bench. So these wordings different for compilers. Okay, so stimulus module normally in theory in books we will mention. In CAD tools, when we are using, we'll be using called as test bench. Okay, then finally the output. Okay, so stimulus module, you are passing the inputs, and that stimulus module we are calling the description. Okay, so it will work out and it will give the output. That output you should verify at the end, right? So in theory books we don't have the waveforms, right? So it will be displayed as an output. Okay, as printf statement. Here we have display system task. Okay, in CAD tools and all, you will have the waveform option. So waveform you can observe. So if input is 0 0, output is 0 or 1, like that. Okay, so this is about the 7 points you need to remember if you do any HDL design. It may be for VHDL also, it may be for Verilog also. Okay, the same will apply. Okay, this is about this 7 points. Okay, so go through once again. So we'll see the example now. Okay, with this idea, and hope you will understand the program in better manner. Okay, so with this we'll begin the gate level multiplexer. So we will design a 4-to-1 multiplexer here with 2 select signals. Okay, so if you know one of the multiplexer, you can do any design. 2:1 mux, 8:1 mux, 16:1 mux, 32:1 mux, 64:1 mux. Okay, and then multiplexer means you have definite relation, right? 2 to the power n to n multiplexer. So you have one here, so it is 4-to-1 mux. Okay, so because 2 select lines are there here, so 2 to the power 2. Okay, so multiplexers serve a useful purpose in logic design. Okay, even your TV channels also have a good example for these multiplexers, right? So at the set-top box, there are many channels are present, right? Just if you switch in your remote, okay, the channel number, so you are going to see that TV channel, right? If you next change the number, you will get another channel, like that. Okay, so it is a big multiplexer, like that it will be working. Okay, they can connect 2 or more sources to a single destination. Okay, so they can also be used to implement Boolean functions. So these are all the usefulness of the multiplexer is explained. So in this design we'll assume, okay, the signals S1 and S0, these are nothing but the select lines. Okay, so based on the multiplexer, 4-to-1 mux you will have 2 select lines, 2-to-1 mux we have 1 select line. Okay, 8-to-1 multiplexer you require 3 select lines. This idea you know already. Okay, so these S1 and S0 do not get the value X or Z. This one assumption we'll make, because Verilog will take 4 values, but if you take 4 values, the truth table may be big, right? So just for assumption, we'll take S1 and S0 will take only 0 and 1 values. Okay, so with that we will proceed with the gate level multiplexers. So what is the first step? What is the first step in when you are writing program? It is an IO diagram and then truth table. Okay, so that we'll see. So the gate IO diagram and the truth table for the multiplexers are shown below here. Okay, the IO diagram, why it is required, will be useful in setting up the port list for the your module. Okay, port list for the multiplexer. You are writing no module name, list of ports. So there this will helpful IO diagram. Okay, and once you know the list of ports, you can declare there which is input, which is output. So first part of the program is over. Then depending on the intermediate variables, you will declare that, and finally we'll explain the functionality. Okay, so that is what. So this is the 4 to 1 multiplexer. The 4 inputs I named as I0, I1, I2 and I3. To select these 4 inputs, you require 2 select lines. They are named as S1 and S0, and it will have one output, the named as out. Okay, so this is the black box representation. This is called as IO diagram or logic symbol. Okay, inside that what is there we don't know at present, but we know the big picture. So it will have 4 inputs, 2 select lines and 1 out. Okay, so that is how it should come to your mind. So anytime when I say 4 to 1 multiplexer means this design should come to your mind. That's it. If you remember this, so next step is all it will follow. Okay, so now since you have 2 input lines, so you can write here truth table inputs, 2 inputs. Just write 2 inputs and write the all possible combinations of 2 inputs. Or 2 to the power 2, it is 4. So 0 0 means it is decimal 0. Okay, so 0 1 means decimal 1, 1 0 means decimal 2, 1 1 means decimal 3, 0 2 3. Okay, so 4 possible combinations of inputs are there. So now how the what is meant by multiplexer, based on that we will write the output entries. Okay, so what is out? Based on the select line, one of the input should be selected. That is what the multiplexer functionality. Okay, so now 0 0 means which input should be selected? I0. 0 1 means second input should be selected. 1 0 means I2. 1 1 means I3. So this is normally will follow, but you can change this. Even you can 0 0 you can select I3, 0 1 you can select I2. Anything you can do accordingly. Your program also changes, your design changes. Okay, so you don't know your no, you have set top box, right? You have a Reliance set top box, you maybe Sky Airtel set top box you have in your home, right? So when you switch the channel, so you will not understand. For a normal people it is just like a number, right? So decimal number you have, but inside that it is an electronic circuit. Okay, it is an FPGA kit there. Okay, so how it is functioning? Based on this logic only. Okay, so based on the number of input. Okay, so for example in your home you have 1000 channels. Okay, 1000 channels you have in your TV. So 1024 is the nearest number, means 2 to the power 10. That means you have 10 select lines. That means 0 0 0 0 0 0 0 0 0 0 to 1 1 1 1 1 1 1 1 1 1. So like that. Okay, so it will be programmed. Okay, so accordingly when you switch that button, so it will change the, so that is switching the button means what? You are changing the select lines. As you change the select line, output will change, so your TV channel will change. Okay, so news channel or entertainment channel, like that it will change. Okay, so hope you understood the concept of mux. Okay, and its IO diagram and truth table. So once you know this, you can write the next part now, that is the Boolean expression. So what is the Boolean expression? How you write for this? Only one output is there, so only one expression you will have out. So now no need of K-map here, so just a simple. So if you are writing a sum of products expression now, so what we'll do, if 0 is there means we'll take complement of that variable. 1 means we'll take variable as it is. Okay, for example now first min term. Okay, what is the product term here? S1 bar, because it is 0, no? So S1 bar, like this we are writing, or else prime also will use. Okay, S1 bar, any method will use like this. Okay, S1 bar. So this is how we have written Boolean expression. Then S0 also 0 is there, so S0 complement, and then you have the input with respect to this I0 is selected. So this is the first product. Okay, so out means what? All the 4 combinations. Similarly you write the second one, it is S1 bar S0 I1 plus S1 S0 bar I2, S1 S0 I3. So this is the Boolean expression, simple. Okay, so this bar sometimes in computer language they don't have this, so they will use prime. Okay, so this is also complement, S1 bar S1 bar I0. Okay, so like this also they will use. Okay, so you'll see the expression and then the logic diagram. Okay, hope it is clear the way I am explaining. So the logic expression for multiplexer output can be written as, okay, so truth table. From the truth table only we are writing this. So something, no magic here. Okay, so first one is to select the first input. S1 bar, S0 bar. That means both select lines should be 0. That's why it is complement. If you are writing product of sum, the things will change. Okay. So it is a sum of product expression. So I0, then S1 bar. That means S1 should be 0, S0 should be 1. Then I1 input will be selected. Then S1, S0 bar. S1 is 1, S0 is 0. I2 will be selected. Then S1, S0 if both are 1, I3 is selected. So all the combination is nothing but the multiplexer output out. Okay. So this is the first example I'm explaining detail. So later on you will understand all the designs. Even the lab programs also will be same way it will be carried out. Okay. We'll implement the logic for the multiplexer using basic logic gates. Okay. So basic logic gates means what? So here you have the complement, right? Complement, to implement which gate you require? NOT gate. Then there are products are there here. 3 terms are there. In each of the products you have 3 terms. So to multiply these each, you require 3 input AND gate. Okay. Second basic gate. Then there are 4 sum are there. So plus is there. So 1, 2, 3, 4 some terms are there. So to add this all 4, you require a 4 input OR gate. Okay. So that's what this is called as basic logic gates. And OR and NOT gates are basic gates. Okay. So using that only you are writing the logic diagram. So the logic diagram for the multiplexer is shown here. We'll look at that. So far it is understood. So you have gone through such diagrams, okay, in digital system design. Okay, so now we'll try to understand. So anyway you can write. So I have taken the horizontal one, and you can vertically also you can draw. Okay, vertically means what? All these inputs will be there upper side. Okay, like that. Okay, so here I have taken the all the inputs. So 2 select lines are there, S0, S1, and accordingly I0, I1, I2, I3. So first we have drawn the lines. Okay, all the 4 lines are drawn. Then based on the Boolean expression, now we are going to connect those lines and making one gate. Okay, for example, first one. Okay, so first we need 2 NOT gates, right, for complementing the S1 and S0. Okay, so that we have named it because I could not write S1 bar here because this is a variable. Now we will be using in programming that character is not allowed, Verilog compiler. That's why I gave it a new name, S1 and S0 n. Okay, nothing but these are 2 new intermediate variables. You have to declare it as wire. Okay, so NOT gate. So now accordingly this also new 2 lines now along with S1 and S0 lines, these 2 new lines. So now for first gate. Okay, so first AND gate, what is the product? It is S1 bar, S0 bar, I0. Okay, so I0 whatever is there, it is connected first, then S1 bar is connected, see here, and then S0 bar is connected. Okay, so this is the first. So this AND gate output should be stored some value, right? For that you have declared the variable y0. Okay, so y is normally used for output, so that's why y0 it is used. Okay, then similarly second is S1 bar, S0, I1. So see here I1 is connected, then S1 bar is connected, and then S0 is connected. See here S0 is connected. So this is the second product named as y1. Okay, so this why it is name required, because we need to instantiate the gates, no? So when I call this AND gate, what is the output? I could not directly use this out, right? Intermediate output where somewhere I should store. So that's why these variables are required. Okay, then third output is S1 S0 bar I2. So I2 is connected, S1 is connected, okay, and S0 bar is connected. Just you can see the connection. Okay, then last one S1 S0 I3. So I3 is connected, S1 is connected, and S0 is connected. It is named as I3. So y1, y2, y3, these are the 4 products now, and these products should be added now. Plus symbol is there. So for that you have the OR gate. So this is the OR gate here, 4 input OR gate, and these are 3 input AND gates. Okay, and these are NOT gates. Okay, so these are NOT gates. So these are the basic gates and or NOT. Using that we are constructing the logic diagram. So output of OR gate is the final out. Okay, so see now the IO diagram and this one you compare. When I draw first IO diagram, you don't know internally what is there, which gates are there, how they are connected, you don't know, right? Just you had the outer picture, right? So you had 4 inputs, 2 select lines and 1 output. Okay, so now if you zoom that IO diagram, so what you got, it is having 2 NOT gates, 4 3 input AND gates, and 1 4 input OR gates. So this design can be done in many ways. Okay, even you can use the universal gates, NAND gates, NOR gates. The circuit may be little complex. Okay, but there are many methods are there. This is one of the method how we can do. Okay, so hope you have understood. So programming part I am not explaining much, because you know already the programming part we have done almost. Okay, everything in the components of the module we have done, but understanding this design is very important. Okay, so that's why, because you have learned in, it may be third semester. Okay, so almost 1 year of gap you have. Okay, so that's why I have taken this part. Okay, so with this knowledge, if you have understood, okay, if you have not understood, you can replay the video. Okay, if you have understood, we'll move forward. Okay, so now with this design knowledge, so we'll write our Verilog description at the gate level. Okay, so how to write the gate level now? Very simple. First thing is module name. You should give one name for this multiplexer. Then you have to list of ports, all the ports you have to write, I0, I1, I2. So for that you have to refer the IO diagram. Okay, this if you refer you may confuse. Okay, even you can refer this, no issues. S1 S0 as the select lines, and all are scalar inputs and output. Okay, all are scalar inputs and output. Then after that what comes, you need to declare which are inputs, which are output. So here input you have to take all these 6 as inputs, and output you have to declare for out. Okay, so that also over. So once declaration is over, then you have to do the intermediate variables. You have taken here S1 and S0 and Y0, Y1, Y2, Y3. This you have to declare it as wire. Okay, not as register, because they are just driving the output of the gate, right? So they are drivers, so you need to use wires here. Okay, so once you have done, so what is next? So your programming part will come. So first you need to write the NOT gate. Okay, so NOT gate means what? It is a one input one output gate. So first you need to write the output S1N, NOT you have to call, and then S1 is the input. Second NOT gate S0 and S0. So then you have to call all the 4 3 input AND gates. Okay, so for that output is Y0, input is I0, and for that S1N S0N. Okay, similarly Y1 Y2 Y3 you have to write, and for final OR gate you have to use these as the inputs and this as the output. Okay, out Y0 Y1 Y2 Y3. Okay, so this is the just the program, very simple. If you know this diagram, easily you can write. That's why we have mentioned there is a one-to-one correspondence with the Verilog description at gate level and the logic diagram. Okay, the logic diagram has a one-to-one correspondence with the Verilog description. The Verilog description for the multiplexer is shown here. The two intermediate nets, whatever I have explained so far, S0 and S1N, are created. They are complement of input signals S1 and S0, and internal nets Y0, Y1, Y2, Y3 are also required. Note that instance names are not specified for primitive gates, not and or. Okay, so these are primitive gates. No, just many times we are calling this. That's why names are not required. It is optional. Instance names are optional for Verilog primitives, but are mandatory for instances of user defined modules. Okay, for example, in the next program stimulus module, you may be writing a top level module and you are calling this multiplexer there. Then you should give multiplexer a instance name, because it is you defined, right? User defined. Okay, whereas these are primitive gates, no need to have the instance name. Okay, this you need to understand clearly. Okay, so with this knowledge, I will just show you the program. Very simple. Okay, so it is a 4-to-1 multiplexer. Module is the keyword. Okay, so now we are looking at the complete program at gate level. Then module name I have given mux 4-to-1. Okay, so I have started with a alphabet, so no problem with this name. Numbers are there, but they are in between. Okay, and there are underscores are there, which is allowed. Okay, like that names you can give, any names you can give. Mux 4-1 you can give, like that. Okay, I have given this name, and then all the list of ports from the IO diagram I have written out I0, I1, I2, I3, S1, S0. And this you can write it in any format. Okay, you can mix it. Input you can write in between, out you can, anything you can do, but all the 7. Okay, 4 input, 2 select line, and 1 out. All 7 should be there in this list of port. That is the idea. Then from this list of ports, you need to declare which is output, which is input. Okay, so out is output here, and then this we have written separately just to understand. This is input signals, this is select lines. Okay, no need, you can combine this in single line also. Okay, So just you need to give space input I0 comma I1 comma I2 comma I3 comma S1 comma S0 also you can write, or you can write separate. Even you can write this input I0 input I1 input I2 input I3 like that. Single also you can write. The Verilog will not compiler will not give any errors. Okay, but this is a normal general look. So when you look that program, it should look neat. Okay, that's why this neatness. Okay, so you have one output, four input lines, two select lines. Simple way writing the port declaration. So then we have the internal wire declarations, wire S1 and S0 n. Even you can use single wire here to write all the 6 signals, but still we have taken it looking better. Okay, so y0 y1 y2 y3 declared as nets. Okay, hope you have understood this part. So once you have understood, now just use the logic diagram picture. So have a pen and paper and write down this. Just simply look at the video. Okay, so make a notes and write it so that you will understand better. Okay, so now first we have to do the NOT gates. So NOT gate output is S1n and input is S1. NOT gate S0 and S0 as I already mentioned. Okay, so just then you have three input AND gates are called. So AND instance names are not required. Y0 is the output, input is I0, S1n, S0n. Whatever signals we have used in this program declared, that only we have to use. Okay, then Y1, I1, S1n, S0. That means S1 bar, S0. Then Y2, I2, S1, S0 n, S1 bar, S1, S0 bar, right? Boolean expression. Y3, I3, S1, S0, all are one, right? So this is how the four gate AND gates are called. Then finally you have to add these products. So for that OR gate you are using out is the output, and the inputs are now output of these four AND gates, that is y0 y1 y2 y3. Okay, so finally you have to make the module end module. There is no semicolon, there is no space here. Okay, in between you have the semicolon to end the sentence. So this is the complete program. Okay, so write down this. The same way we will be doing it in labs also. That's why I have not started the lab programs yet, because you should understand this logic first, only then we can able to start. That's why I have taken very fast to cover up the two modules. Okay, so because the programming part starts in module 3, so that's why I have come here. So once I started now, I can go slow now with programming, and I can parallelly start now HDL lab also. Okay, fine. So next, this is over now. So just program is over, we are running it. If any programming errors are there, okay, grammatical errors are there, compiler will throw the error. That type of error we call it as syntax errors. Okay, so if I am writing somewhere made mistake, colon I missed. Okay, while typing it may happen, right? So such things it will notify, that is syntax error. Now we need to check another type of error, that is semantic errors we say. Okay, so what is this semantic error? So I have designed a 4:1 multiplexer. Is it working like a 4:1 multiplexer or not? If it is working something else, then my design is wrong, right? So I need to verify that. For that I have to write the test bench. That means I need to pass now inputs values to the four inputs, and then two select lines I should give, and I should check is it properly selecting. When I give 0 0, it is selecting input line 1 or not. Okay, so that is what the stimulus module is about, or test bench. Okay, so this multiplexer can be tested with the stimulus shown in example below. The stimulus checks that each combination of select signals connects the appropriate input to the output. That's what I mentioned. Okay, when you give 0 0, it should connect I1 to. Okay, so for example, in your remote now, when you click, so 301 channel, I don't know what is the channel you are getting. So whichever you are getting till yesterday, it should get same channel, right? So now earlier there was a local channel, so the numbers were changing, but now you have the Tata Sky or Airtel TV, the channel number. So if you go to your aunt's house or somebody else's house also, if they are using the same receiver of Airtel or Tata Sky, the same number will holds good, right? On the same number the channel is coming, the same channel which you are watching, right? It may be the IPL whatever you are watching match, or it may be a serial of your choice, right? So that is what the complete design we say. Okay, the signal output is displayed one time unit after it changes. Okay, that means in the stimulus module I have used output as a variable. Okay, so that is in capital letter I have used. Okay, because small letter if I use, it is a keyword, right? It is not allowed. So that's why capital I have written, case sensitive, so to understand it. Okay, so there one second delay I have given, one time delay. So after that your every input changes will be shown. Okay, so system task dollar display we have used in this stimulus module, but even you can use the monitor. What is the difference between monitor and display is display we need to give every time. Okay, monitor one time if you write it is enough. Monitor means continuously monitoring, display means every time we need to display. So that also we try to show you in this program. Okay, so many things are cleared here with this one program, that's why it may be going lengthy. Okay, so module stimulus, so name anything you can give here. Okay, module top or module test, anything you can give. Then inputs you have to give as register now. Okay, because it is a behavioral model now. Okay, stimulus, so register I0, in1, in2, in3, then register s1, s0, all the inputs are given register. Then output should be declared as wire. Okay, then we have to call the multiplexer, so mux 4 to 1, this is we designed, right, user designed, that's why instance name should be given compulsorily. Okay, otherwise it will throw error. Then you have to pass. Okay, this is here connecting by port and connecting by name and connecting by ordered list we have learned, right, in ports. So this is by connecting by ordered list. Here see, here output is there, here also output given, there I0 was there, here in0 was given, in1, in2, in3, s1, s0. So this should be properly followed. Okay, otherwise you should follow the connect by name concept. Okay, so this is where you should be careful whatever you have given there. Okay, so once you have done, you have to pass the values now. Okay, so initial keyword we are using, so about this we will learn in behavioral modeling, don't worry about this. Initial, begin. Okay, we need to give some values now. Okay, so because since it is a test bench, we could not give all the combinations, right, 4 inputs, 0 0 0 to 1 1 1 1. So any one combination I'm using, so such one combination I have used here, 1 0 1 0. Okay, 1 input 1 is 0, input 2 is 1, and input 3 is 0. Okay, then I have used a display here, every time display. So whatever I have given here, that will be displayed now, in 0, in 1, in 2, in 3 will be displayed. Next what I have to do, I have to just change the select lines, and I need to see output is getting these values or not. Okay, in 0 is 1 is there, 0 is there, so the same value is getting or not, I need to check. So for that I will next select the s1 is equal to 0, s0 is equal to 0 I will give, and that I will display. S1 is same thing, whatever I have given it will display, and output now it will compute. Okay, based on your design. Okay, so multiplexer whatever you have written logic diagram, if that logic diagram is correct, then output will be coming correctly as this one, because when 0 0 means in0 should be selected, the output should be 1 here. If it comes 0 means your design is wrong. That is how we will verify the design. Okay, so in CAD tools and all we have the this one waveforms, so no need of this much thing, but in syllabus they have told you need to understand writing test bench also. Okay, that's why we'll learn this. So similar way we'll change the select lines now. 0 0 is over, next we'll do the 0 1. So see here 0 1, and the same thing will be displayed here, and output should be now I1 whatever value. Okay, similarly to choose in2 I need to give select line 1 0, the same display line is copy pasted here. Okay, so no changes. Okay, so next 1 1, so like that. So all the combinations we have verified. So the display is every time we are writing here 4 times or 5 times you have written, but if you use monitor here, so monitor every time you change the value, one of the value here, it will change the output what it will show. No need to write display 5 times. That is only the difference between display and monitor. Okay, so hope you have understood this. Okay, so end, because initial begin we have shown, right, here initial begin I have shown here. So to end this we need to write one end, there is no semicolon also for this, and then module we have started, so for that end module we have to write. Okay, so this is the test bench waveform. So you go through once again whatever I have explained so far. Okay, if so now we have given display, right, so what is the output it is going to show. Okay, so that output will tell you the design is correct or not. Okay, so just we'll verify the output. So this is the output. The output of the simulation is shown below. Each combination of the select signals is tested here. First we have given 1 0 1 0, then we have changed the select lines, so output is selected first in0, then in1 is selected as 0. Okay, see here, then in2 is selected for 1 0 combination, and 1 1, IN3 is selected. Okay, so any combination you can, so you can change the design now. Okay, you can write your own program now. You can give here 1100 now. Okay, another combination. So then you have to check. Okay, like that. So in software industry, testing job means this only. Okay, so somebody will be designed the program, so you need to test now all the 16 or 10 to the power 10 1024, okay, combinations, whatever, you need to test it individually and you have to check the design is okay or not. Okay, so that is what about this. Okay, so with this, hope you have understood now. So when I say next 4:1 multiplexer, so all that 7 thing I told you in the very beginning, so that will be clear to you now. Okay, first you have the IO diagram. From IO diagram you are writing truth table. So then you have the Boolean expression, gate level diagram, then Verilog description at gate level, then you write the program. Okay, so you have the stimulus module and finally the output. Okay, so in CAD tools this will be shown as a waveform, so that we will see in the lab part. Okay, so with this, this is a lengthy video so far. Okay, so go through once again if you have not followed. So next class we'll do the 4-bit multi adder, that I can go quickly because now you have understood this procedure. Okay, steps. Okay, so the same way we'll do that one in the next video. Okay, so thank you for listening. We'll meet in next video. Okay.